We present COAST, Constraints and Streams for Task and Motion Planning. Our first contribution is a faster method for task planning with streams. We use streams from PDDL stream, which are unit sampling functions that provide an interface from motion planning to task planning. In prior work, generating symbolic objects for streams leads to an exponential task planning time. In our method, we overcome this limitation by creating stream objects after task planning, using a direct stream planning algorithm. Our second contribution is connecting constraint-based planning like from IDTamp to stream-based motion planning like from PDDL stream. This allows us to use efficient constraints that can prune the search space of TAMP. We use IDTamp and PDDL stream as our baselines. This is the block domain, which is adapted from IDTamp. The goal is to move the red block into the center with only a side grasp. Here we show an example with 3 blue obstacles. We show examples of solutions with increasing difficulty, and we plot the total time spent planning with the number of obstacles on the x-axis and the logarithmic time on the y-axis. Our approach shows the best performance compared to both PDDL stream and IDTamp. This is the kitchen domain adapted from PDDL stream. The goal is to transfer items from one region to another, where the blue region is the sink and the red region is the stove. Here we have an example of 4 cook and clean goals, where 2 objects need to be transferred to both the blue and red regions. We show examples of solutions with increasing number of goals. Our approach shows the best performance compared to PDDL stream by 2 orders of magnitude. This is our third domain, which is adapted from PDDL stream, where the goal is to send analyses of rocks and images of objectives to the stationary lander via line of sight. The challenge is that the rovers cannot cross the divider, so the planner needs to decide which rover should travel to certain rocks or objectives. We show more examples of the rover domain with increasing difficulty from left to right. The first row represents our solution without caching. Without caching, our method refines each action with unique stream objects, even though many positions for line of sight can be reused, since all of the rocks, landers, and objectives are fixed. With caching, we can reuse positions across the task plan, similar to PDDL stream. The first plot is comparing task planning time of our method with and without caching and PDDL stream. We can see that our method is an order of magnitude faster than PDDL stream. In the second plot, we plot motion planning time. PDDL stream is more efficient than our method without our caching enabled, but slightly worse than our method with caching. Lastly, we compare the total planning time. We can see that the task planning time for this domain is relatively insignificant, since there aren't many movable objects. In motion planning, we perform worse than PDDL stream without our caching, but with caching we can achieve faster performance. Thanks for watching.